Hello, it's good to see you back. In this video we're going to understand about resistors. So first let's talk broadly about what are the different categories of resistors. You can categorize resistors into ohmic resistors and non-ohmic resistors. Ohmic resistors are ones that follow Ohm's law. So we can say these follow Ohm's law. And when you say it follows Ohm's law, what we imply is that if you draw the IV graph, you will get a straight line. So ohmic resistors follow this kind of relationship between I and V. Non-ohmic does not follow Ohm's law. And the graphs, an example graph can be between IV, can be something like this. It can be something like this. So let's see what are ohmic resistors. So the first set of examples are the wires. Then there are normal resistors that you use in electronics. And then things like fan, etc., or other electrical equipment. So you can say equipment. And in this we don't include the heaters. The heaters and toasters and bulb, things that gets heated up, generally, they are ohmic in some sense. They can be for linear in some area like this, but beyond a certain point, as current increases, as the temperature increases, these things exhibit non-ohmic characteristic. That means that the relationship between IV is no more linear. So I'll say heaters are examples of non-ohmic, and typical non-ohmic resistors are also diodes and transistors. So in diodes and transistors, you have, initially there are not much free electrons. As you give a slight voltage, it gets a lot of free electrons and suddenly its resistance drops. In this video, we are going to study more about the wires, which are just one category of ohmic resistors, and how they behave for various parameters. Now let's assume we have a wire made up of a specific material with a cross-sectional area of A and length L. Now, depending upon the type of the material, the number of collisions that happens as the electrons move around will be more or less. So the material property of this wire determines how much resistance this wire is going to offer, and that property we call it as resistivity. So this is resistivity, and then it also depends upon the resistance, also depends upon the geometry, and the geometry is defined by the length and the cross-sectional area. So as the length increases, you have more electrons have to traverse a longer path, and hence there will be more resistance. So length and resistance have a linear relationship. But if your area increases, you can imagine that your electrons can navigate through more easily. So they have a inverse relationship. So this is how your resistance of a wire is defined. Your unit of resistivity is given by, R is ohm, is resistivity into meter, which is length, by meter square. So that gives you resistivity is ohm meter. So that's a SI unit of resistivity. Let's look at a visual representation of this equation. So resistivity, which is a material property, as it increases, for example, aluminum may be a little higher, or maybe non-conductors, maybe the resistivity may be even higher. So as the resistivity increases, you have resistance increasing. As your resistivity goes down, for example, for copper, the resistivity may be quite low, silver even lower, gold, etc., very low. So you have resistance also going down because of resistivity going down. And as the length increases, you can see that since it has to traverse more, the resistance increases, and as area increases, the resistance decreases. So this is a great way of visually imagining what happens. Now finally, let's look at the relationship between resistance or resistivity versus temperature. Generally for ohmic conductors, you can imagine that as temperature increases, the electrons are going to be moving much more faster. So your resistance or resistivity increases with temperature. So you can imagine that it'll be something like a straight line. It increases with temperature. Now, as you decrease this temperature, you may have at 0 Kelvin, absolute 0, so you cannot go lower than this. You may find that there is some residual resistance in some material. But in some material, there may be no residue resistance. So the resistance, so let's say for tin and lead, you may find that at 0 degrees Celsius, the resistance is 0. So this, we call it as superconductivity. So at this 0 Kelvin, your resistance is so low, it offers no resistance, and it has some great applications, wherein like making magnetic levitation or designing circuits. If you can design circuits with very low resistance, it could use very less power. You could increase speed, etc., etc. So these are called superconductors, and it so happens that for certain other kinds of materials, you may find that they can achieve superconductivity at temperature which is not 0. So it could be like this. So this you could these are examples are mercury. So at about 4.2 Kelvin, so at this is not 0, it achieves resistance is 0. And for lead, at about less than 7.25 Kelvin, 7.25 Kelvin, your resistance is approximately 0. So this temperature at which the resistance is 0, we call it as transition temperature. So let me summarize again. Superconductivity is a property wherein at a particular temperature for a material the resistance becomes completely 0, so it becomes very conductive. And for material like lead and tin, it happens at 0 Kelvin. For other materials like mercury and lead, it may happen at a slightly higher temperature. I hope you enjoyed this video. See you in the next one. Bye.